Okay, so now let us continue. This is something, it's just a definition. A permutation that can be expressed as a product of an even number of transpositions is called an even permutation. A permutation that can be expressed as a product of an odd number of transpositions is called an odd permutation. Yes? So, is the idea clear? So for example, what type of, so if I give you alpha on S3, so let us say that this is alpha 1, 2, 3, and I give you 2, 3, and 1. If I ask you, is alpha even or odd? So how do you answer this question? So how? You have to write it as a product of transpositions and see what happens. The first thing you do is probably to write it in a cyclic form. So what is the cyclic form of it? 1 goes to 2, 2 goes to 3, 3 goes to 1. This is 1, 2, 3. And then, because this is just one single cycle, do you remember the formula, the general formulas? The intuitive one is usually easy. So we write it as 1, 2 times 2, 3. Do you remember? That was the decomposition. So how many of them are involved? 2. So 2 is even, so we say alpha is even. Another tricky way is also something is good, you know, you connect 1 to 1, you connect 2 to 2, and you connect 2 to 3 to 3. This is called an inversion. How many intersection points you see? 2, and that's even. If it turns out to be odd, that's an odd one, okay? This is also some books define it in that way, odd or even, based on the inversion that happens. But in the exam, you just use it, you just write it in a decomposition. One more question. Do you think identity is even or odd? So epsilon. Do you think epsilon is even or odd? Yes?
It's even.
Why?
Because, I mean, multiple reasons. But main one being, there's 0 intersections. If you do that, and it's
one of them, yeah.
0 cycles, and it's positives of the.
No, but based on what I told you, the 0 intersection, I agree with you. For example, epsilon, I can write it as 1, 2, 2, 1. Do you agree?
Yes.
And because this one has 2 and 2 is even, no matter how you do it, you will end up with even number of cycles. So the identity, and this is the way that the book has proved it. The book has already first proved that epsilon is even, and then use this as a lemma to prove that all permutations are either odd or even. Okay? So you can read it yourself. But is that understandable? Yes? Okay. So now let us see what we have here. Yeah, this is simple. So if I give you a cycle, this is what is the content? The remark from remark 2 and theorem 4, we conclude that a cycle of length n is even if and only if n is odd. Yes? You see, if the number of, if I have an R cycle with R elements in it, if R is even, the cycle is odd, and the other way around. Because you can write it as a, for example, I told you that if you have A1, A2, up to AN, how can I write it? I can write it A1, AN, multiplied by A1, AN minus 1, and it goes to A1, A2. So how many transpositions you see in this decomposition? N minus 1. Yes? Because this is 2, 3, up to n. So that's n minus 1. So the number appear here, and the number of the transpositions involved differ exactly by 1 unit. Is that clear? Yes? Okay. So now let us go to the next one. This is a good theorem to know. The set of even permutations only in Sn forms a subgroup of Sn. Can you see why? So far, what we learned is that if you give me a permutation in Sn, there are two possibilities. Alpha is even or alpha is odd. Okay? And then what we do, we put all even ones in one bag, we put all odd ones in another bag. My claim is that the even ones, the bag containing the even ones is a subgroup, not the one containing the odd ones. And you see why? Yes?
Because epsilon is in the even one.
What, pardon?
Because epsilon.
Yes,
The
first of all,
identity is
it
in
should
the
contain epsilon. Because
even.
if it is going to be a subgroup, it should contain the identity element, which is epsilon. But we just learned what is epsilon. Epsilon is an even one. So epsilon will not be here. So definitely this one is not a group because it does not contain the epsilon. That is obvious. This is not a group. Not a group. But just because this contains epsilon, there is no guarantee it is a group. It contains epsilon. But we have to check all the criterion for being a subgroup. What are they? It shouldn't be empty, yes? Yes, it is not empty because epsilon is there. So epsilon is here, so this is not empty.
Closure.
It should be closed under multiplication. So why is that true? So, by the way, there is a name for it. This is called A sub n. This is called symmetric polynomial, symmetric group of degree n. This is called alternating group of degree n. Degree n. So our claim is that A sub n is a subgroup of S sub n. So it is not empty because epsilon belongs to an. We learn that an is not empty. But now let us imagine I have two permutations here. Alpha is in an and beta is in an. I want to convince myself that alpha beta belongs to an. Why is that true? Yes?
Because since both alpha and beta are basically composite on
Even number of
exactly,
permutations.
exactly. Yes.
If I juxtapose them, put them
Yes.
next to one another, even plus even becomes even. So it means alpha beta is composed of how many transpositions? Even number of transpositions. So it should be in A sub n. Is that right? So that's also true, but this is not finished. One more. If you give me alpha is in an, I want to convince myself that alpha inverse is also in an. But that's also true. Do you remember? Based on which theorems? If alpha is an means what? So it means alpha is equal transposition 1, transposition 2, up to transposition 2n. Even number of transpositions. Yes? And if I ask you what is alpha inverse is tau 1, tau 2, tau sub 2n inverse. But how should I write this? Do you remember socks and shoes theorem? So I should write tau 2n inverse, and I go up to tau 2 inverse, tau 1 inverse. Yes? But what is the inverse of a transposition? We had an inverse of any cycle. We wrote it the other way around. So the inverse of any transposition is again a transposition. So it is a transposition. How many transpositions I see? Even. So this means alpha inverse is also a product of even transpositions. So alpha inverse is also even. So this is also true. So remember, this is a subgroup of Sn, but these ones are not. But there is one more theorem. Do you remember what was the order of this group? We had this last time, and one of you actually answered. You answered.
N factorial.
N factorial. So that was n factorial. Do you remember? Now I want to ask you one question. What is the order of this? Because now it is a group. I am allowed to talk about its order. Now I am asking. So what is the order of the alternating group? What is that? Many of you probably want to answer this one. Yes? This is correct. Yes, n factorial over 2. So it is very strange. Half of them are even, half of them are odd. But it is not trivial. Don't think that because something is either even or odd, sometimes we intuitively compare it with even numbers and odd numbers. Yes? So we say that half of them are even, half of them are odd. This is not in general true, but in this case it is, but we have to prove it. Can you feel how to prove it? This kind of method is very simple, but I want you to learn it. So I define a function for you, f, from an to, this is not a standard notation, but let me use O for odd ones. Okay. And what I want to do, I want to say that let me pick alpha from here. I want you to give it as 1 and 2 alpha. Okay. So I want to define a function for you from the set of even permutations to the set of odd permutations in this strange way, that if I pick one alpha from here, you just multiply it by 1 and 2. Of course, n should be greater than or equal to 2, because I want to have 1 and 2 there. Okay? First of all, do you feel this is a good way of defining a function? Do you remember how, if you are good in algebra, the first question you ask, this tells you that this is a function, takes an element from here, which is an even permutation, and send it to the odd permutation, to the set of odd permutations. Am I respecting myself or not? So what is this? Is it guaranteed this is odd? Because if this is not guaranteed to be odd, I have problems with even defining my function. But is this guaranteed to be odd? Why? Because alpha is being picked from here, which is even. And then when I multiply it by one extra, 1 and 2, this becomes odd. So this means that from definition point of view, I haven't done something wrong. It is sensible. Is that right? But my claim is that f is bijective, and you have to show it for yourself. F is bijective. This is the claim. If you manage to prove that f is bijective, what is the consequence of proving f is bijective? Yes?
With an equal amount of odd and
Yes, they are into one-to-one correspondence. So it means that how many elements you have here, you have the same number of elements there. That's the meaning of one-to-one correspondence. And because the totality is n factorial, if I can show that these numbers are the same, so it means the number of elements here is the totality divided by 2. So this I want you to prove yourself, which is extremely simple. So you should be able to prove that this function that I defined here for you is a bijective one. Is that clear? So now that is the last part of this. Yes, this is the definition, and this is the formula. Okay, but this is left up to as an exercise. Please do that. Any questions?
Sorry, the order, do you mean the order of the set or the order of the...
Yeah, if I have a group, if it's a finite group, it means the embedding set of the group is finite, and by the order I mean the number of elements in the set of the group.
Okay, not how many times it should multiply.
No, that is the order of an element of the group.
Yeah.
Yes, these are different. Usually we use the same notation for it, but they are different. Okay. So, any questions here? So this one is a very important lesson. Hopefully we can manage to some extent here. Isomorphism and Cayley's theorem. Okay. The first thing I want you to know is the definition of isomorphism. So let me explain it on the board. There is no point to read the text. So let me explain it on the board. So what is the meaning of isomorphism? So it's a Greek word. Iso means the same, morphism the same, form. Morph means form, iso the same. So it means the same form. Okay? So that this topic is relevant if I have two groups, not one group. Okay? So let us say that I have one group G1 with its own binary operation. I call it a star sub 1. And I give you another group, I call it G sub 2 with its own binary operation. So I have two groups involved. And I want to define what do I mean by the groups being isomorphic. So I would say that G1 is isomorphic to G2, and I wrote it in this way. I write it in this way, G1 is isomorphic to G2. Or if I want to emphasize on the operations, I can also write this. It doesn't matter. If you really want to emphasize on the binary operations, you can pick one of them. When I say that I have two groups that are isomorphic, what do I mean? It means someone can find a bijective map from F1 to F2. It means, so this means two things. One, there is a bijective map F, for example, from G1 to G2. Okay? Two, for every pair of elements in G1, F of A star 1B becomes F of A star 2 F of B. That's the meaning of being isomorphic. So first of all, I want to make sure that you understand what does it mean. You see, A and B are chosen from G1. If I want to do a binary operation between them, that binary operation should be the binary operation from this group, yes? Because A and B are picked from G1. But now, after F applies on A, I go somewhere in G2. And if F applies on B, I go somewhere in G2. If I want to combine them with a binary operation, that binary operation is not the same binary operation here. It should be the binary operation there. So if this is the case and this is the case, I would say that these two groups are isomorphic. Okay? And by the way, proving that a group is not isomorphic is very strange. It means that there is no bijective function with this property. Yes? So I want you to understand if you want to. So let me give you an example first. Might be it is very simple to understand. What does it mean intuitively? It means that they are carbon copy of one another. If I want to give you a metaphor, for example, if you want to learn a language, in a dictionary, you have some words in Arabic, for example, you have some words in Swedish. So you can make sentences in Arabic, but then you can actually send them to Swedish and you have your sentence in principle. So somehow when I have two isomorphic groups, in principle, it means that I have one carbon copy of that group. Yes? That's the meaning. So it means that if I want to study a group, if I am comfortable with working with the group, I will work with the group, or I will find another one which is isomorphic to it and I will work with the isomorphic one. So exactly like that, if I am comfortable with English, so I will do English and then I translate my essay to any other language. So you can do whatever you like in the field that you are more comfortable, and when it is done there, you go back to the other realm. So for example, I want to give you an example here. So let me write Z4. Do you remember what is Z4? Z4 is a group 0, 1, 2, 3. And what was the operation? The operation was adding modulo 4. This is a group. And do you remember I gave you another, this group is also famous for us now. We have worked with it several times. Do you remember what is U10? U10 is the number of elements less than 10 which are whose GCD with 10 is 1. So one of them is 1, the other one is 3, the other one is 7, and the other one is 9. But the operation here, do you remember what was it? It was multiplication modulo 10. So you see, the elements are not the same. They have some elements in common, but they are not all the same. And the operations are quite different. Here we add and find the remainder. Here we multiply and we find the remainder. So here we find the remainder by 4. Here we find the remainder by 10. But my claim for you is that these two groups, even though they are different numbers and different number operations, one of them is a carbon copy of the other one. So I want you to. So it means that if you are comfortable to understand this group, you can work in this group and translate it back. Or if you are comfortable with the other one, you can work in the other one and translate it back. So what is exactly the meaning of this? Okay, so my claim is that these two groups are isomorphic. I want you to get a picture of it. So if you don't mind, let me draw the table of Z4, table of operation. You can do it, yes? 0, 1, 2, and 3. And then I have 0, 1, 2, and 3. So it doesn't take that much time. So let us fill up this table. So every time I add and find the remainder by 4. So 0 plus 0, 0, 1, 2, 3. 1 plus 0, 1, 1 plus 1, 2, 1 plus 2, 3. But 1 plus 3 is 4. 4 by 4 is 0. The remainder is 0. And then 2 plus 0 is 2, 3, and then 0, and then 1. And then 3 and 4, which is 0, and 1, and 2. That's my table. Yes? Okay, so let us be patient a little bit and do the same thing for U10. Okay, so I would write it as multiplication modulo 10. 1, 3. So if you don't mind, I know that this is a little bit weird, but I have some problem. Instead of writing 1379, if you don't mind, let me write 1397. It doesn't matter. 1397. And let us fill up this table together. I have to consider all possibilities. So it doesn't matter if I write them in order, this is the natural order, or I write it in this way. I want to know how this operation acts. So for example, 1 times 1 is 1, 1 times 3 is 3, 1 times 9 is 9, 1 times 7 is 7. But 3 times, this is 3, 3 times 3 is 9. But can you tell me what is 3 times 9? It is modulo 10. It is 7. And then 3 times 7 is 1. And now I multiply 9 by 1, 9, 9 by 3, 7, 9 by 9, 3, 9 by 7.
9 by 9.
Not 9 by 9, sorry. 9 by 9, 1. Because I am doing it by 10. And 9 by 7 is 3. And then I have 7, and then I have 1, and then I have 3, and then I have 9. Yes? So this is not something mysterious. I am doing the tables for these two groups. But now, my claim is that this is just a relabeling of this table. But you have to be clever and find the relabeling correctly. So what I am telling you is that go to this table and do this change. Send 0 to 1, send 1 to 3, send 2 to 9, and send 3 to 7. Okay. This I have already done it at home, so this is why it's in my memory. I am using it. So that is why if I send it randomly, it might not work. Isomorphic, it means you can find a relabeling that changes this table totally into this table. Okay? So hopefully, if I haven't done something wrong, let us do it together. Let me change my color. So everywhere I see 0, I put 1. Yes? Everywhere I put 1, instead of 1, I put 3. Yes? Everywhere I see 2, I put 9. And finally, everywhere I see 3, I put 7. So if I haven't done something wrong, these new colors are exactly these numbers. Yes? So this means that even though the sets were different, the operations were quite different. Here I add and find the remainder by 4. There I multiply and find the remainder by 10. But they are not, they are more or less, one of them is a carbon copy of the other one. So that is the notion of isomorphic. Okay? So as an exercise for this problem, I want you to, by the way, some of you, do you feel that this is a bijection? Because you know that for being isomorphic, I have to arrange them in a bijective manner. So you see that this function, which I call it f, is bijective. Yes? Because, every one of them has one single arrow going out, and every one is receiving exactly one arrow, and all of them are covered. So this function that I defined here for you is a one-to-one and onto map. And what it did, it also respect this condition. You understand that? That's the meaning of being isomorphic. Of course, usually we have to write a function. You can go home and think about it. I think you can come up with this function, f from z4 to u10, f acting on x is the remainder of 3 to the x by 10. If you insist to write a function in a mathematical form, I think this is the correct form. But this is good enough because that is a one-to-one and onto function. So is that understandable? Okay. Now let us go to the next one. So this is the example I solved for you. Let me solve this one as well. Show that the groups R and addition and the group R positive and multiplication are isomorphic. Okay? One thing I want to mention is that it could be extremely hard to prove two groups are isomorphic. Why do you think it is the case? Which part of it is hard? Yes, come up with a nice function. Because you want a function which is one-to-one and onto, surjective and injective, and also respects the operation. It should preserve the operation. So, but if the example is hard, I will give you a hint, as I have done it in the homework. The last homework is related to isomorphism. It is not that easy to come out of the blue with the function, so I have given you the function, and I'm asking you to check that this is isomorphism. Is that right? Okay. So, for example, I want to rely a little bit on your intuition. This is not very hard. Can you tell me, so what is this telling? This is telling you that I have two groups. One is just the whole set of real numbers with plus. I hope that you immediately see that this is a group. But the other one is R positive and multiplication. R positive means all positive numbers. So if you want R positive means 0 to infinity, not including 0. And this is just multiplication. You already know this is a group, but do you agree this is also a group? Yes, because multiplication is associative and if I, by the way, if I pick two positive real numbers, multiply them, it is a positive real number, so closure is done. It is always associative. What is the identity here? 1, and 1 exists there. And what is the inverse of every number? Because 0 is not there, it's 1 over that number. So it's a group. Now the claim of this is that you need to prove that these two groups are isomorphic. It's a classic example. Can you come up with the function yourself? Because what you need to do in these kinds of problems, you have to have an idea about your function, which is bijective and respecting the second condition, and then prove that it respects the second condition and it is bijective. So somehow you want to do that what? You want to change addition to multiplication. So what do we want to do? So let me write it like this. Let us say that f is my function. This is a scratch paper work. So I go to a scratch paper, I try to find that function. So I want a function so that when it applies on R with addition, and it gives me something in R positive, even though if I pick a negative one, I still want to go to positive side with multiplication. But in a way that f acting on A and B with this operation becomes equal to f of A, f of B, but with which operation? The operation on the right hand side. Is that understandable? This is the way I think. Okay, I'm not saying that this is easy to come up with the function. But I hope that this is, if you just look at this structure, can you guess what function it should be? I want a function that maps all real numbers only to positive real numbers in a way that addition somehow changes to multiplication when I go from right to left. What type of function you have that changes? Yes?
Maybe writing something in the same base and then using the potences.
Exponential function.
Exponential functions.
Very good. And usually, what is the base? Because we have infinitely many exponential functions. Which one we usually choose in mathematics? E. L. Yes, that's it. So you see that by this way of thinking, I was able to guess a function like this. I'm not saying that this 100% works, but it was better than nothing. So this is our educated guess now. If I have my educated guess to prove that they are isomorphic, what I have to do? To show that this function is one-to-one, and injective and surjective, if you're familiar with those words, and it respects this condition. And that's very easy now to prove, yes? Do you agree that this function is one-to-one? Is it injective? What is the meaning of being injective? It means that if x1 and x2 are chosen from R, and if I know f of x1 is equal to f of x2, can I conclude that x1 is equal to x2? The answer is yes, because this means e to power x1 is equal to e to power x2, and everyone knows that if this happens, x1 is equal to x2. So it is injective. Is it surjective? How do I prove surjectivity? I have to show that any number that I choose on the right-hand side, there exists an element in the left-hand side such that f of x becomes y. I want to confirm that this is indeed the case. This means surjectivity. But is that right? If you give me a positive y, which x is mapped to that positive y? ln of x. Yes? So and that is very clear. So if you give me y, I will say that x is ln of y. And f of x becomes f of ln of y, which becomes e to power ln of y, and that is y. So this is surjective. Surjectivity is also done. And the next thing is that f of x1 plus x2, I have to convince myself this is equal to f of x1 multiplied by f of x2. But that's also very easy, because f of x1 plus x2 becomes e to power x1 plus x2, and I can write it as e to power x1 multiplied by e to power x2, but e to power x1 is f of x1 multiplied by f of x2, and weird. But if the group is complicated, it's not that easy to come up with an educated guess. So this is why if the question, for example, like the homework is hard, I will try to give you myself the function, and I want you to confirm that that function makes a one-to-one correspondence, makes an isomorphism. By the way, the function itself is called isomorphism. Two groups are called isomorphic, if you can find something like this.
A question.
Yes, please?
Is it like always isomorphic in one direction, or can you go like
No, of course, that's a good question as well. So can anyone answer this question? So the question is that, should I go from, for example, how should I know that I have to write this one on the left, this one on the right? Yes? So why shouldn't I do it the other way around? Might be the other way around is easier to come up with. So that's okay if you can do that. Why this doesn't matter?
Since the bijection.
Yes, it's bijection. If it's a bijection, we had one theorem that its inverse is also a bijection. And it will also respect that condition. So that's a good exercise to do.
So you don't have to check like f
No,
a
it
times
depends.
b.
You have to make up your mind first.
Okay.
And according to what you did, you have to define your function.
See.
But it doesn't matter if you manage it to do it in this way, that's okay. If you manage it to do it the other way around, that's also okay. Yes? One question. What happens to the identity here? If I have an isomorphism, isomorphism will start mapping every element from the left group to one single element from the right group. My question for you is that, if I feed an isomorphism with the identity of the left group, what do you think it will give me and why? Is the question clear? So the question is that, if I have an isomorphism, and then I pick E1 from here, do you think that there is a definite answer for f of E1? And if so, why? Yes, it's E2. But can you see why this is E2? Remember, isomorphism sends identity to identity. Yes?
You put zero in the function.
In this case, yes. No, in general.
Okay.
So you see that, yes, you are right. The identity element here was 0. The identity element here is 1. F sends 0 to e to power 0, which is 1. That's correct. But this is, I want to claim that this is always the case. Yes, please.
F of A star B, F of A star E, E1 must equal to F A star 2 F E.
So what you are saying is that f of A E1, and by the way, we just dropped the stars.
Yeah, sure.
In the book, you will not see F star 1, star 2.
Yeah, sure.
On the right-hand side, they don't put any star. On the left-hand side, you don't put any star. But you need to understand, the operation on the left is from first group. The operation on the right is the first group. So if I want to write it, what do I write? I would write it as f of A, f of E1 on the one hand, because it is isomorphism. On the other hand, what can I write for this?
This is just
Because
F.
A E1 is just A. Yes? So, and then tell me why this is correct. F of A is equal to f of A, f of E1. And then what we want to conclude, that f of E1 is indeed E2. Why this is correct? Yes?
Because anything using the what part?
Cancellation.
Yeah, cancellation by star 2.
Yes, it's cancellation. So I can cancel f of A from the left-hand side. And here f of E1 is left, but when I cancel on the left side, this is a group, this is an element of this group. So what is left is E2, not E1. Yes? So remember, for example, if I have f of A2, if f is an isomorphism, what do you think will be the result of f of A2? Yeah, just say everyone, you can say. What is f of A2 if f is an isomorphism? Can I bring 2 out?
It's F A.
So this means it is f of A times A A squared means AA. But because F is isomorphism, you write it as FA. But be careful, this operation is done on G1. This operation is done on G2. We both of them write simply because we are lazy. By the way, it's very efficient. And then I have something multiplied by itself, so it becomes F of A to power 2. So there are many things you can conclude yourself. For example, if you know the order of an element from the left group is n, is it possible to prove that the image has order n as well or not? So you can sit down and think. There are very nice exercises in the book, and the exercises are very simple. Any questions? So do you understand the meaning of isomorphism? Okay. Let us see what else is left. So I think we stop with this because this is a checkpoint. This is a good one. So here, intentionally, I haven't given you the function. But I hope that it shouldn't be so hard for you to guess the function. You see, this is a group of matrices, and then I have a group of complex numbers. And I want to tell you that these two groups are isomorphic. So if you want to study, for example, complex numbers, you can ignore complex numbers and work with matrices. And whatever result you get with matrices, you can translate it back into the language of complex numbers, because they are identically from group point of view. So if you couldn't guess, of course, we can discuss about that again. So this is an extremely important theorem. I just tell it because this is a very, very beautiful theorem. I will do it next time. And that is Cayley's theorem. For example, by the way, Cayley's theorem, I can give you a question in the exam, formalize the Cayley's theorem. So what I need, you just write every group is isomorphic to a group of permutations. So this is a very, very deep result. Can you feel it? What does it mean? I just want to ask your opinion. Every group, this claim, by the way, this is a very deep result with a very astonishingly simple proof. But he was genius actually to come up with the isomorphism. And this was not very, you will see the proof is very simple. But do you see why this is a very deep theorem? Why? Every group is isomorphic to a group of permutations. Group of permutations we studied in the first part. Why this is a deep theorem? Okay, why it's a very shallow theorem? So why it's a deep theorem? Yes.
It describes every group.
Yeah, so it means that if you want to study all groups, you can somehow study groups of permutations, because every other group is isomorphic to a group of permutations. So in principle, if we study groups of permutations deep enough, we more or less know everything about every other possible group, which, by the way, is a very deep result, because so far we have seen a lot of different structures. We label them as groups. The elements are different, the binary operations are different, but this claim is a very big claim. This claims that every group, no matter which group is it, it's isomorphic to one permutation group. Not the permutation, the totality, not every permutation. A subgroup of that totality is isomorphic to a group that you are working. So in principle, if you study groups of permutations deep enough, you know everything about every group. Is that right? Okay. So we will come to the proof of this theorem next time. Thank you very much.